You know, in just about any industrial setting, there's this one critical safety part that gets misunderstood all the time. The difference between a pressure safety valve and a pressure relief valve. Yeah, they sound almost identical, but getting them mixed up, well, that can be the difference between a system running smoothly and a total catastrophe. So let's break down why this is so important. So let's get right to it. Are a PSV and a PRV just different words for the same gadget? It's a super common question, whether you're on the plant floor or in the engineering office. And the answer is a big fat no. They are not the same, and understanding why is absolutely crucial for keeping things safe. And hey, this isn't just a mistake for beginners. This quote right here proves it. Even pros who've been in the industry for years can end up using these terms like they're interchangeable. It might seem like a small detail, but believe me, that one little mix-up can have some really, really bad consequences in a high-pressure situation. All right, so to clear all this up once and for all, let's properly meet our two pressure protectors. We're going to define exactly what each one does, because it all comes down to how they act when the pressure starts to climb. Okay, first up, we have the pressure safety valve, or PSV. I want you to think of this one as the emergency eject button. It's built for stuff that expands like crazy, things like steam and gas. When the pressure hits its limit, a PSV doesn't just crack open a little bit. Nope, it pops wide open, instantly. It's exactly like the safety valve on your pressure cooker at home. It lets out a huge blast of steam to keep the whole thing from blowing up. Its only job is immediate, massive relief. Now, on the other side of the coin, we've got the pressure relief valve, or PRV. This one is way more of a careful manager than an emergency button. It's designed for liquids, stuff that doesn't really compress, like water or oil. A PRV opens up gradually, in proportion to how high the pressure gets. So if the pressure creeps up just a bit, the valve opens just a bit. Its goal isn't to stop a giant explosion, but to manage and stabilize the pressure in the system to prevent things like pipes from bursting. And that right there brings us to the absolute core difference, that sudden, violent pop versus a slow, steady, proportional opening. And this isn't just a tiny design choice, it's the fundamental engineering principle that makes these two devices completely different beasts. So yeah, it all boils down to pop action versus proportional action. A PSV's pop is designed to get expanding gases out of a container fast before they can blow it apart. A PRV's proportional action is all about carefully bleeding off pressure in a liquid system to keep things stable. The choice isn't just a suggestion, it's dictated by the pure physics of the fluid you're dealing with. But you might be wondering, how does a PSV actually get that signature pop? Well, the secret is this really clever piece of internal design called a huddling chamber. As the valve starts to lift, pressure rushes into this special chamber, and that instantly creates a massive secondary lifting force that just slams the valve fully open. A PRV is built completely differently. It just doesn't have this pop action mechanism. Okay, let's just quickly sum up the key differences here. The PSV, that's for compressible stuff like gas and steam. It uses that pop action to prevent a catastrophic failure. Think steam boilers. The PRV, that's for incompressible liquids like water or oil. It opens gradually to maintain stable pressure in things like hydraulic systems. It's simple. The number one rule is always match the valve to the fluid. And the consequences if you get this wrong, they can be really severe. For instance, if you put a pop-action PSV on a water line, when it slams shut, it can create a destructive shockwave called a water hammer that can literally shatter pipes. On the flip side, if you use a gradual PRV on a steam boiler, it might not vent the pressure fast enough to stop the whole thing from rupturing. This isn't just a matter of bad engineering, it is a serious, direct safety hazard. To really see what this looks like in the real world, let's dive into a case study. This is where all the theory crashes into the hard reality of industrial safety. So, picture this, a high-pressure power plant. The piece of equipment we're focused on is a superheated steam boiler, and it's protected by what everyone thinks is a properly working pressure safety valve. Everything seems fine, until a control system suddenly goes haywire. Here's the play-by-play of the failure. First, the pressure starts climbing, and it's climbing fast. It hits the 950 psi set point. That's the exact moment the PSV should have popped wide open. But it doesn't. Instead, the valve just simmers. It starts leaking a little bit of steam, but it never fully opens. Because of that, the pressure just keeps on rising, blowing right past the safety margin until a backup system is forced to shut the entire operation down. So, what on earth happened? Well, the investigation found a tiny but critical error. Turns out, during routine maintenance, a technician had adjusted the blowdown ring incorrectly. Now, that little ring is the key component that makes the pop action work. And that one single wrong adjustment effectively turned a pop action PSV into a gradual acting relief valve. A total disaster for a high-pressure steam system. And here is the absolutely terrifying result of that one mistake. Because the valve only simmered instead of popping, its actual flow rate was 60% below the capacity needed to protect that boiler. A catastrophic explosion was avoided only because that secondary shutdown system kicked in. It was a huge near miss, all caused by a fundamental misunderstanding of how the valve was supposed to work. So how do we stop this from ever happening? Let's take everything we've just learned and distill it down into a really simple guide for choosing the right valve every single time. Honestly, it just comes down to asking yourself 3 questions. First, what's your fluid? Is it a compressible gas or an incompressible liquid? Easy enough. Second, what's your goal? Are you trying to prevent a massive explosion or just control normal system pressure? And third, what kind of action do you need? An instant all-or-nothing pop or a gradual, controlled release? Your answers to these questions will point you to the exact right device. No guesswork needed. At the end of the day, the difference between a PSV and a PRV isn't just about using the right word. It's not semantics. It is pure and simple physics. It's about matching the mechanics of the valve to the physical properties of the fluid it's supposed to be protecting. You get that right, your system is safe. You get it wrong, and you are taking a massive, massive gamble. And that brings us to our final and most critical takeaway. That case study showed us that a valve that was close enough in name was absolutely nowhere near close enough in function. In safety engineering, precision isn't just a nice to have, it's the only standard that matters. Which really makes you ask, what is the true cost of close enough?